Hi, everyone. My name is Claire Simpson, and I will be presenting about my project titled Forecasting Post-Fire Vegetation Change using ConvLSTM networks and remote sensing. To frame the problem I'm going to tackle, so fire regimes in the Western US are changing, and in the past decade, we've had some of the largest and most severe wildfires on record. And these changes have implications for our society as well as ecological communities. So in light of changing fire regimes, it's really important to know about what happens to the land surface after a fire. The land surface processes that occur after a fire often include vegetation recovery, and this refers to successional changes initiating and new vegetation growing back. And this vegetation growth is essential with respect to ecological and hydrological processes, soil erosion, local microclimates, and many more things. And my hope is that a better understanding of these post-fire land surface changes can help improve the management of burned areas. My research question guiding this project is, to what extent and at what temporal scales can ConvLSTM networks forecast patterns of post-fire vegetation change? And I have this figure here to show where I'm going with this. So this figure shows a time series image of a burned area for 5 years after a 2016 fire. The variable on this map is the Normalized Difference Vegetation Index, or NDVI, which is derived from satellite imagery. And this is used commonly as a proxy for vegetation health. The goal of my project is, given 10 years of monthly time series imagery, to forecast monthly NDVI and leaf area index, or LAI, which is another proxy for vegetation recovery. And I'll be forecasting these variables at monthly intervals for the 10 years after fires. The first step in this project was developing a data set to reflect my goal. I extracted imagery tiles at all fires that occurred in the Western US between 2010 and 2012. Each of these images is a 6-band image with red, green, blue, near infrared, NDVI, and LAI bands. My dataset ended up being composed of almost 1,000 multi-band, multi-temporal images at the locations of 1,000 fires. I split these images into training, validation, and test sets. And then in my pre-processing stage, I tiled these images up to 24 by 24 pixel subtiles. So my entire dataset ultimately contained almost 10,000 subtile images. The model inputs for my baseline model are 10 years of monthly composite images through 2 months of images after the fire. And then the model outputs an almost 10-year NDVI and LAI imagery time series. And this is also at monthly intervals, where the prediction begins 3 months after the fire. And this figure on the right shows this model concept. My first experiment involved determining how accurate a model trained with only 15 time steps would be compared to training a model on the whole time series. And then the smaller model would only predict 15 time steps as well. And the practical utility of this is that while having a long time series output is ideal, some applications would benefit more from a more accurate forecast in the short term, such as in the context of immediate post-fire land management. The second experiment involved dropping 4 of the predictor features from my training data set to determine whether the red, green, blue, and NIR bands were really necessary for accurate model performance. The red and NIR bands are both represented in the NDVI equation. However, the green and blue bands aren't, so I was curious about whether this additional information would be important, especially given that we might expect the green band to reflect vegetation growth. My results show that a ConvLSTM is suitable for this type of forecasting task. The MSE on my test set is 0.381. The shorter time series model performed worse than the baseline model. The test MSE is only 0.43. And my interpretation of this is that the model had less data to learn on, and so you can kind of see it's overfitting to the data, and the lower volume of data must have outweighed the fact that this model had an easier task of predicting fewer time steps. The model with only 2 input features performed better than the baseline model. And so this kind of indicates that these non-vegetation-based bands are relatively unimportant to predicting vegetation indices. And this knowledge is useful when creating future data sets. As a last note, looking at all these loss curves, the MSE does seem to be continuing to decrease. So training these models beyond 200 epochs might be beneficial later. Here's an example of an LAI time series prediction from the model. The prediction is in the right column, the target is in the left column. And this is data from 8 months through 1 year post-fire. Here's a similar example of an NDVI time series forecast. And you can see here, the model is capturing some of the visual patterns, though it doesn't exactly match the target. In conclusion, to summarize the outcomes of this project, the model performance declines when fewer time steps are included. The RGB and NIR bands are relatively unimportant. And overall, I'm excited about the possibilities of using ConvLSTM for predicting post-fire recovery, as they've demonstrated promising results here. Bibliography, data sources, thank you very much.